160 plus megabits per second, so it's really fast. Let's confirm that the file exists using lsltrh home1 swap file 1. There it is. Now if you're concerned about what the file looks like internally, less home1 swap file 1, and it tells you it's binary. So there's nothing much we can do with it. Now we need to turn on the file system, the swap file system. So step 2, which we'll list as B, is to execute make swap followed by the path to the swap file, which is home1 swap file 1. This overlays the swap file system in this file. So just like we did before, if we recap the earlier steps, we enabled swapping using a partition by creating the partition, then using make swap to overlay the swap file system, then using swap on to turn on swapping. Similar process. This is just a file instead of a partition. So let's go ahead and make swap, and there it is. It's set up swap space on the file just like that. The exit status returned is a success. It's a 0 value. So let's move on to the next step, which is to turn on swapping as far as the kernel is concerned. So make swap overlays swap file system. The next step, swap on, followed by the full path to the file, makes swap space available to the kernel. Now before we enable swapping, let's confirm the existing swap space. Free-m is one way to do it. This tells us that there's about half a gig of swap. Swap on-s reports on the devices that currently constitute swap. So SDB2 is the lone device. Now we're going to throw a file into the pool by using swap on home1 swap file 1. We'll echo the exit status. It looks good. And then we'll re-execute swap on-s. Now we see that in addition to dev SDB2, beneath home1, which is indeed mounted on dev SDB1, there's a file named swap file 1, which is also roughly half a gigabyte. Thrown into the pool of things, if we execute free-m, we'll see we now have about a gigabyte worth of swap space available. And we can keep adding swap space. Free tells us whether or not the operating system is using it. Currently, the OS is using almost 100% of its random access memory, which is a good thing. This means most of its work is occurring within RAM. But inevitably, as more users or as more processes and/or more processes are launched on the system, the kernel will be forced to resort to virtual memory to page in and out items from random access memory. And it does so using a variety of algorithms, but nonetheless, it will at some point need the space, which is why we need to ensure that enough swap space is available. So again, we now have a file and a partition. We also need to ensure that when the system reboots, this swap file is made available. So task 2 is to ensure that when the system reboots, the swap file is made available to the kernel. And to do so, as you may have guessed, we'll simply nano etc fs tab. But the syntax is slightly different. In there we'll place the path to the swap file, which is home1 swap file 1, and be sure to do so after the mount of the home1 partition, followed by the same options, swap, defaults, 00. This is what will be placed into the file. So with that said, let's take a look at the etcfs tab file. We'll clear screen here, reset the buffer, then nano etcfs tab, and also this will help if we execute swap on-a. Again, you want the swap space to be made available after the mount of home1. Otherwise, the boot up process will be unable to find home1 and the swap file. So again, full path, home1 swap file 1, type swap, defaults 00. That's all that's required. And we'll include a comment that this is an additional 512 megs swap file, and it's located in the home 1 mount point. So let's save the changes, and we misspell swap file, so let's go ahead and just fix that. Otherwise, when the system reboots, it will throw an error trying to make the swap space available. Now let's take a look at that swap space again using swap on S. We'll turn off swapping on the file using swap off, swap file 1, echo the exit status, then rerun swap on -S followed by free M, and we're back to about 500 megs. Now we'll execute swap on -A to force a read of the etcfs tab file, and it throws a device or resource busy because the existing partition is in use. However, now when we execute free M, we see that we're back to a gig worth of swap space, and swap on -S will confirm as such, which means, again, if you execute swap on -A and it mounts your swap space, it means when your system reboots, it will mount it for you. Now just a quick note about the two columns we haven't discussed, used and priority. Used reflects what you'd see when you execute free-m. When we executed it, 0 was being used, or 0 bytes of the roughly a gigabyte were being used. So that's self-explanatory. Of each swap point or swap space, whether file or partition, you'll see how much is used. Priority ranges from low to high based on values that are low to high. So it matches accordingly, which means a higher value has a higher priority. -3 is a greater value than -6. So the operating system is more inclined to swap using a partition as opposed to a file. You can influence the priority if for some reason you think, let's say, the file would be faster. Using swap on -help, you'll see how you can influence the priority using -P to turn on a given priority. So for example, let's swap off home 1, swap file 1, and then re-execute swap on -S. Now we turn on swapping using home 1, swap file 1, but we want the priority to, let's say, be 10, which is a greater value than -3. Now when we execute swap on -S, which is in our history, you'll see that the OS is more inclined to use swap file 1 as opposed to SDB2 because we've influenced the priority. The OS by default will choose what it thinks is the faster option, which generally is a partition over a file, when allocating virtual memory. So we've set up our system to reboot and start with swap space. We know how to define a swap based on a file as well as a partition. It's very straightforward, nothing much to it. Just know that the process is the following. If you're creating a file, use DD with the dev0 interface or the dev0 facility. Set your byte size to 1024 and then just multiply it out until you get the size that you like. So if you wanted a 1 gigabyte swap file, just indicate a count that would reflect as much. Or you could indicate count 2 gigs and it does it as well. For example, let's just show you briefly how to create a 2 gig file using DF, or DD that is. So task 3, create 2 GB swap file. Taking the recently used command, instead of indicating byte size, we'll just tell the count to be 2 gigabytes using 2G, and then execute this from the shell. But we'll call this one swap file 2, of course. We don't want to overwrite or risk clobbering the existing file. And providing there's enough space, which there should be, in home 1, we'll create momentarily a 2 gigabyte file. And you can watch the file grow by opening another shell to the server. And this will create a 2 gig file. So you could say count equals 2G or count equals 512M, and you'll achieve the same result. Or you can multiply byte size times count and end up with an appropriately sized file. Once you have that file, enable swapping, or provision the file as a swap file. Last but not least, enable swapping in the kernel by using swap on. And to recap a partition, use fdisk or parted to set up the partition. Type 82 Linux of a size that makes sense, 512 megs, a gig, so on. Make swap to overlay the swap file system to denote that it's a swap partition. Then make the swap space available to the kernel by using swap on. And then of course update etcfs tab so when the system reboots it will auto mount the swap space for you. Let's see where we are with this 2 GB file. It's still creating it, and if we were to SSH from a separate shell to 75.199, we'll navigate to home 1, and then LSRTH, you'll see the file as it's growing. We could even watch it grow using the watch command, which is another neat program we've neglected to mention. So for example, watch lsltrh swap file 2 will update every 2 seconds, which will reflect changes in the file. So add watch to your list of important Linux commands. It allows you to run the command on a interval. The default's at 2 seconds, but we can change the default. It's a great utility to watch, let's say for example, the appending of information to a log file. So watch space tail space the file name will cause tail to be refreshed every 2 seconds. And here we see the file is being written, 2 GB, and it should stop growing, and then the process in the background will momentarily stop. It appears to be a little bit bigger, but it will stop momentarily, and we'll have access to our file. So that's it. We'll just go ahead and kill this process, the watch. This will be done momentarily. And if we wanted, we could kill this at this particular stage, and the file still could be used as a swap file. So let's go ahead and kill it. It's wrapping up anyway, and it tells you it made it up to this size, and it'll be done momentarily. Performed at a rate of 17 megabytes per second. So that file can be provisioned as a large swap file as well. So we've covered swapping as well as basic file system allocation. It's really straightforward, nothing major to it.